Hello and welcome to the logic of it all. In this video, we will talk about linear search and binary search. Let's start with linear search. So the problem is we are given an array that or any kind of sequential data structure like a vector or a list. So an array of values and a specific value v that we call the target value. And the problem that we are trying to solve is whether v occurs in the array, and if it does, where in the array it occurs. Now, what linear search does is a very simple algorithm. So if this is our representation of the data structure, like an array, what linear search does is it starts from the beginning of the array and compares the value in the first position with the target value v. And if it finds it there, it returns the index 0 and says, I found it at index 0. If not, it moves on to the next position, index 1, and compares the value at that index with the target value v. And again, if they're equal, it returns 1 as the position of the target. If not, it moves on to the next position and so on. So it continues doing this, and you can imagine this can be implemented with a simple loop. And the algorithm terminates in two possible ways. It's either that somewhere along the way at some index, let's say j, it finds the value that is exactly the same as the value you're looking for. And in that case, it returns that index j and terminates. Or it could be that it goes through the data structure, the array or the vector, all the way to the end, and it never finds the target value v anywhere in the sequence. And in that case, it returns something that represents the failure of the search. So for example, it can return -1. So that's the idea of linear search. It's a very simple algorithm. And to go through this in more detail, imagine your sequence being this sequence of integers 2, 3, 5, 5, 7, 8, 11, 15, 18, 25, 29, and 32. And the target value v is 29. So we are looking for 29 in this sequence of integers. So if you want to execute a linear search, what we need to do is we need to compare the first value in the sequence, which is 2, with the target value. They're not equal, so we go to the next one, compare 3 and 29. They're not equal, so we go to the next one, and so on. And the question is, how many comparisons do we need to make until this algorithm terminates? And if you actually go through all the steps, you'll see that we have to go through all these numbers, next one, next one, next one, all the way to here, until we find 29 equals 29, and that requires 11 comparisons. Okay, so that's linear search. Now, what you may notice is that the reason that we needed so many comparisons was that the value that we were looking for was stored towards the end of the sequence or array. So in the worst case, it could be that you have thousands and thousands of elements in your array, and the value that you're looking for, your target value, is stored as the last or very close to the last element. And in that case, linear search performs very poorly because you have to go through all the elements and until all the way towards the end until you find the target value. So the natural question to ask is there a better way to do this? And that's where binary search comes in. Okay, so the setup is kind of similar, more or less, to linear search. So we have a sequence of values and we're looking for a target value in that. So it's a search algorithm, it's a search problem. The only difference in the setup is that we have an extra assumption, and that is we assume in binary search, we assume that the input sequence, the sequence that we are performing the search in, is already sorted, which means that the values are either in an increasing order or decreasing order. And that's the requirement for for binary search to be applicable. Now, if that's the case, then this is how binary search works. So again, this is my representation of, let's say, the array that we are searching. And let's say this is index 0, this is index, let's say 11, and then index 1, 10, and so on. Okay? Now, what binary search does is that instead of starting from the beginning of the array, it starts from the middle. Okay? So to find the middle index, we take the average of the first and the last indices. So 0 plus 11 divided by 2, that's 5.5. We round it down to 5. So we go to index 5 and we begin from the middle value. And we do the same. We compare the value that we find there. Let's call that x, value in the middle of the sequence. We compare that with our target, v. And you can imagine that there are three possibilities. It's either that we are very lucky and the value that we see in the middle of the sequence is exactly our target value. In that case, you return the index of that middle position, in this case 5, and you're done. You found the search is complete. Or it could be that the value that we are looking for, v, is smaller than the value that we see in the middle. So v is less than x. Now, this is where this assumption that we made becomes important. Because we assume that this sequence is sorted, let's say in an increasing order, it means that everything that comes after x, everything in the second half, is at least as large as x. So it's x or higher. Which means that because v is less than x, it means that v is going to be less than everything in the second half of the sequence. Which means if we want to continue the search to the next iteration, we don't need to search the second half of the array because everything in the second half is going to be greater than v, and there is no point in searching there. So what we do is, what binary search does, is it makes a recursive call, but only in the recursive call, it only searches the first half of the sequence. Okay, so that's another possibility. And finally, the last possibility is that the value that we are looking for, v, is greater than the value in the middle. So it could be that v is greater than x. Now, following the same kind of reasoning, it's easy to see that in that case, there is no reason to search what comes before x because everything before x is smaller than x, and as a result, smaller than v. So v cannot occur in the first half, which means in this case, our recursive call is going to be only on the second half of the array. Okay, so in these three cases, it's either that we are lucky and we immediately find the target value, or we need to make a recursive call either on the first half or the second half of the sequence, which means after each recursive call, the size of the sequence gets halved. And as a result, even if you start with a very long sequence of integers, let's say 1,000 numbers, after the first iteration, it reduces to 500, then 250, then 120, then 62, and so on. So you can see that very quickly the size of the sequence becomes very small, and then the algorithm terminates. So that's binary search. Now, this is, to be more precise, this is an implementation of binary search. So just to explain how this code works. So array here is the array that we are applying the search in. Key is the value that we are looking for, so that's the target. And low and high are the indices that we start the search from and end the search at. So if this is my array, initially low is going to be 0 because we start the search from the beginning, and let's say 10 is the high index. So that's the end of the array. Now, here's how it works. First, we find the index for the middle of the sequence by taking the average of high and low. So 0 plus 10 divided by 2, that's 5. So that's the middle index. And this is the base case where if high turns out to be less than low, it means that the search failed and we return -1, which means that we didn't find the key in the array. Now, this is where the actual search happens. So as we said, the first thing that we do is we compare our target with the value that we find in the middle of the array. Now, if they're equal, then we return the index of the middle, in this case 5, and we are done. Otherwise, then we have the two possibilities. It's either that key, the target, is less than the value in the middle. So if what we are looking for is less than this x, then what we need to do is we need to perform the search in the first half. And that is done by this recursive call. So we recursively call binary search on the same array with the same target, and the search this time happens in the first half of the array. So it means it starts from 0, so it starts from index low and ends at the index before the middle. So 4 in this case, or in general, middle -1. Now on the other hand, it's possible that the value that we are looking for, our target or key, is greater than the value in the middle, and that's the final else. And in that case, we need to make a recursive call on the second half. So that's your recursive call, same array, same target, but this time the search starts from the index after the middle. So in the case of this example, from index 6, or in general from middle +1 all the way to the end, which is high. So that's binary search. Now, to make it more precise, here's the sequence, the same sequence as before, and we are still looking for the same target, 29, and this time we want to apply binary search. So if we want to put the indices, so we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So the first step is taking the average of the low and high. Low is 0, high is 11. So middle is 0 plus 11 divided by 2, that's 5.5. We round it down to 5. Then what we do is we go to that index 5, and the value we find there is 8. And our target is 29, which is greater than 8. And that means we need to continue the search on the second half of the sequence. So here. And that's the next recursive call. So this time the low index is 6 and the high is 11. So 6 and 11. We find the middle, which is index 8. We go to index 8. The value that we find there is 18, and 29 is still greater than 18, which means that we need to make another recursive call again on the second half of this sequence that we did. Now we do the second half of that, so here. And that means that the search starts at index 9 and ends at 11. So from 9 to 11, the average of those two is 10. So what we do is we look at index 10. And this time, the value that we are looking for is exactly the same as the value that we find at that middle index. And that means that the search is done. We return that index, which is 10, as the place or position that we found the target value. And note that here we only needed to make 3 comparisons. 1, 2, 3. So only 3 comparisons is needed compared to 11 comparisons that we needed when we tried to solve the same problem using linear search. So the question is, how do these two algorithms compare? Okay, based on the examples that we just saw. So what we saw through these two examples, in the same example using linear search and binary search, we saw that linear search requires much more number of comparisons compared to binary search, 11 versus 3. And that's because if the value that we are looking for is towards the end of the sequence, then linear search starts from the beginning and needs to compare the target with every element until it reaches towards the end where the target is. And that means that in a technical term, we need order of n number of comparisons. Now n here refers, so this is big O, order of n. I'm not going to describe exactly what this is, but intuitively, n here is the number of elements that we have in the sequence. So it says more or less in the worst case, you need somewhere in the order of n number of comparisons, or it requires that much time to perform this task, and that's for linear search. Okay, so if you have 1,000 values, you may need 1,000 or something in that order of comparisons to perform linear search. On the other hand, for binary search, things happen much faster. In the example, we saw that with 3 comparisons, we were able to find the target. Now, in general, we say that the time that binary search takes, or the number of comparisons it's used, is order of log of n, logarithm of n. And the reason that this logarithm comes in here is because every time that we make a recursive call, the size of the sequence gets halved. Okay, so for example, if you have 1,000 values in your sequence, in the worst case, you need order of log base 2 of 1,000, which is 9 comparisons, 9 or 10 comparisons to perform binary search compared to 1,000 comparisons you need for linear search. So we know that log n is much smaller than n, especially when n becomes larger and larger. So that means that binary search is much faster than linear search. So then the natural question is, why do we even need to know about linear search if binary search outperforms it significantly? And if you think about it, binary search requires some condition, and the condition is we are only allowed to use binary search if the sequence is sorted. If it's not sorted, then binary search may not give you the right answer. Okay, so that's the catch here. You are only allowed to use binary search if the sequence that you're doing the search in is sorted. Okay, so here's an example. The sequence is 2, 10, 4, 3, and 9, and the target that we are looking for is 3. And obviously 3 occurs in this sequence here. But because the sequence is not sorted, right, 2, 10, that increases, then 4 decreases, and so on. So it's neither increasing or decreasing. Because of that, if you apply binary search, and I will leave that to you as an exercise to actually go through the steps of binary search, but you will see that if you apply binary search, it tells you that the search fails and it's not able to find 3 in the sequence. So that shows that binary search can be applied only when the sequence is sorted. And if it is, then there is no reason to use linear search because binary search is going to be much faster. But if the sequence is not sorted, then you either need to apply linear search or you need to sort the sequence first and then apply binary search. But as we will see later on in this module, sorting a sequence can be time consuming itself.